5 minutes to show you a hybrid, rigid-soft, wearable lower limb exoskeleton. If you take a closer look at how humans walk, you'll notice something interesting. Different joints play very different roles. For example, when walking uphill, the knee joint is mainly responsible for bearing load and supporting the body, while the hip joint is primarily in charge of lifting the leg and swinging it forward. This leads to a key question raised by a research team from Heidelberg University in Germany, a question that's surprisingly often overlooked. If different joints have such distinct functions, does it really make sense to assist all of them using the same mechanical approach? That question is exactly the starting point of this work. The researchers designed a lower limb exoskeleton, but not the kind that's rigid from head to toe. Instead, it's a hybrid system that combines rigid and soft components. At the knee, they use a rigid exoskeleton structure paired with pneumatic actuators. This setup is specifically meant to support the knee during ground contact and weight bearing, essentially helping to hold the knee when it matters most. At the hip, however, the design takes a completely different approach. Here, the system uses a soft, clothing-like exoskeleton, where cables gently pull on the thigh to help lift the leg during walking. This soft assistance makes the motion feel more comfortable and more natural. By matching the mechanical design to the actual function of each joint, this hybrid approach aims to provide support that's not only effective, but also intuitive to wear and move with. Let's start with the hip joint. Unlike traditional exoskeletons, there are no rigid rotational axes or hinge structures here at all. Instead, a cable transmits the force generated by a motor to the front of the thigh. What's interesting is how restrained this design is. It's not trying to take over your hip joint. It's only there to give you a gentle pull when you actually need to lift your leg. Put simply, when you swing your leg forward, the cable helps share part of the load. But when your foot lands on the ground, when you need stability and support, the system almost completely backs off, barely intervening and without interfering with your natural movement. So why not make the hip rigid? The reason is straightforward. The hip joint has high degrees of freedom and very complex motion. Forcing a rigid structure to align with it can easily restrict natural gait, or even make you feel like you're being dragged along. By using this soft, one-directional assistance, the system only provides help at the right moment. The result is assistance that's more efficient and much more comfortable to wear. That brings us to a key question. How does the system know when it's time to lift your leg? This is where a clever control method comes in, called an adaptive oscillator. You can think of it like one of those dashboard nodding dog toys in a car. You don't need to tell it, this is step 1, this is step 2. Instead, it learns your walking rhythm directly from your body's motion, and then synchronizes itself automatically. Because of that, the assistance feels smooth. There's no sudden tug, and it's never a beat too late. Now let's move on to the knee joint. And here, the design philosophy is almost the complete opposite of the hip. The knee's motion is relatively simple. It mainly flexes and extends. But during walking, especially in the stance phase, when the foot is on the ground, it has to bear a very large portion of the body's weight. For this reason, the research team chose a rigid exoskeleton structure at the knee, combined with pneumatic actuators, rather than a soft solution. You can think of the pneumatic actuator as a cylinder that can push and brace. When your foot is on the ground and your body needs support, it actively helps to prop up the knee, taking part of the load off the muscles. There's an important engineering detail here. The assistive force at the knee is not applied at a single point. Instead, it's distributed through the exoskeleton's thigh and shank frames, spreading the load across the body. This allows the system to provide sufficient support while also improving safety and wearing comfort. To verify this design, the researchers carried out a dedicated set of experiments. They asked 7 healthy participants to walk on a treadmill at a normal walking speed on a 15-degree incline, and compared 4 different conditions: walking without an exoskeleton, assisting only the hip, assisting only the knee, and assisting both the hip and the knee. Let's first look at muscle effort, measured using electromyography or EMG. The results are very clear. As soon as knee assistance is turned on, the knee extensor muscles in the thigh show a noticeable reduction in activation. And when both the hip and knee are assisted, the muscles responsible for lifting the leg are further relieved. Just as importantly, muscles that are less relevant to the walking task are barely affected at all. This shows that the system isn't helping everywhere indiscriminately. It provides assistance where force is needed and stays restrained where intervention isn't. If we zoom out and look at overall energy expenditure, the conclusion becomes even more intuitive. When both the hip and knee are assisted, people completing the same uphill walking task consume about 15% less energy. And this reduction is clearly greater than what you get by assisting only a single joint. To sum it all up, the real strength of this paper isn't about using the most complex algorithms. It's about thinking clearly from the very beginning. Different joints are meant to do different jobs, so an exoskeleton shouldn't force one single solution onto all of them. Be rigid where strength and support are needed, and soft where freedom and comfort matter. That balance makes the system more energy efficient, less awkward to wear, and much closer to what a truly human-centered exoskeleton should be like.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.